Course 3, Lesson 10, we're looking at rational numbers and equivalent fractions. So your goal is to determine if a set is open or closed, which numbers are rational, and find some equivalent fractions. We'll do this pretty quickly. So first, let's look at a set of numbers, the whole numbers. Now we can put this in set notation by putting some brackets around these. Okay, we have our counting numbers and 0, but we don't have any negative numbers. Here we are looking at if a set is open or closed. Now, being closed means that if we take two numbers in a set and do an operation on them, the outcome will also be in that set. So let's try an example. If we add any two whole numbers, is the sum a whole number? So we're looking at addition. Well, think of any two whole numbers, add them together. So let's say I take 3 and 13. I add them together and get 16. Well, that's another whole number. And I could continue showing you examples on, and none of them would give me something outside of the whole numbers. So we would actually say that the set of whole numbers is closed for addition. That is telling me that regardless of any whole numbers that I choose, if I add them together, I will get another whole number. What about for multiplication? If we take that same 3 and 13, we will get 39, which is another whole number. Even if we took 3 and 0, two whole numbers, and got 0, 0 is still a whole number, so we stay within our set of numbers. So we would say the set of whole numbers is closed for multiplication. Let's look at another set. So what if we look at the whole numbers for subtraction? Are they closed under subtraction? Well, let's think of two numbers. How about we pick the numbers 3 and 13 again, but we subtract them? Well, in this case, I get negative 10 as my answer, and you have to think, is negative 10 a whole number? And the answer is no. This is an example where the whole numbers are open under subtraction. Open under subtraction. Because when I subtract two whole numbers, I get something outside of the whole numbers. I just need one example to make it open. There are many examples where it does work. Even if we did 13 and 3. That gives me 10, and that's in the whole numbers. But regardless, I have an example where it doesn't work. Therefore, subtraction is open for the whole numbers. Think about division. If we take two whole numbers, 3 and 5, and divide them, do we get another whole number? And the answer is no. We get 0.6, which is not a whole number. So we would say that the set of whole numbers is open under division. Closed, remember, means if we take two numbers in a set, do an operation on them, we will get another number in that set. Where open, we take two numbers in that set, and we have an example where we don't get a number in that set. We call that open. Okay, so think about some of these other sets, things like integers, okay, are addition, subtraction, and multiplication will be closed, but division is going to be open because we have examples like negative 1 divided by 2. Unfortunately, that does not give me another integer, so division is open for the integers. Okay, let's think about now our new set of numbers, the rational numbers. Now, a rational number is a number that can be expressed as a ratio of two integers. Really, all this is saying is a rational number is a fraction. And as you can see, we have fractions like 1/2, maybe negative 3/4, maybe 5/6, or 10/3. Those are all rational numbers. But so are my integers, my whole numbers, my counting numbers. Because all of those, even if I take negative 3, negative 3 can be shown as negative 3/1. So we have rational numbers with all of my whole numbers, integers, counting numbers. And if we look, our set of rational numbers is closed under addition, subtraction, multiplication, and division. But we have to be careful with division, okay, because we can't divide by 0, all right? Dividing a number by 0 does not work, okay? So, if we look at a number, our rational form is always an a over a b. We're not looking for mixed numbers here. So 3 can be shown as 3 over 1. 73 hundredths can be shown as 73 over 100. Negative 1.4, we could say this is 1 and 2/5, right? Because 4/10 reduces to 2/5. But we have to have it not as a mixed number, so we say this is negative 7 over 5. And lastly, we turn this mixed number into an improper fraction by saying it's negative 43 over 8. Okay? Always showing our rational numbers as one integer divided by another. All right. Let's now move on to our equivalent fractions. Now, this is how we go about comparing and ordering fractions. We find the least common multiple of the denominator. We change both fractions to have the same denominator. We then can compare and order them. And finally, we turn the fractions into their original form. Now, if we are comparing 2/3 and 3/5, we look at those denominators, 3 and 5, and we say, what is the least common multiple? And as you know, that would be 15. Well, we need to change 2/3 to have a denominator of 15. And by multiplying by 5 over 5, I'm not necessarily changing 2/3, just changing what it looks like. But what's great is that it gives me a denominator of 15. We can do the same with 3/5, but instead of multiplying by 5 over 5, we multiply by 3 over 3 to give us that denominator of 15. Now that we have 10/15 and 9/15, we can see that that 10/15 is greater. And when we turn it back into the original form, we can see that 2/3 is greater than 3/5. So finding that common denominator and changing each fraction into an equivalent fraction so we can compare them. Let's just do a couple of these. You can see the answers here, but I want to show you why these work. So let's look at 5/8 and 7/12, this one right here. Well, if we look at that 8 and 12, we know that 24 is a multiple they have in common. So I'm going to get this 5/8 to have a denominator of 24. Well, 3 times 8 is 24, so we have to multiply by 3 over 3. And for the 7/12, we would need to multiply by 2 over 2. So we get 14 over 24. Well, that means that 5/8 is greater than 7/12. Okay? You can look at all of these and follow the same procedure to find equivalent fractions so that you can compare and order your fractions. All right? Now, if we look at something like 18/48 and 3/8, are these the same? Well, they sure don't look the same, but there's a couple of ways to show that these are equivalent fractions. One is to say I could take this 3/8 and try to find a denominator of 48, and we could by multiplying by 6 over 6. So we get 18 over 48. Or we could divide each of these by 6 and get 3 over 8. So we have equivalent fractions. All right, so just another example of what you can do here with these equivalent fractions, all right, to get some so that you can compare and order your fractions. I hope this was helpful for homework and for studying.